Okay, so this is part two of that Unit 5 progress check. I'm not sure if it caught the answer for number 15, but the answer should be B. All right, I'll go into 16. All right, so these are the different Maxwell Boltzmann distributions. So you see the curve for the different numbers of particles. T1, that's going to be the lowest temperature of this bunch. The lower temperature has a narrower distribution. Higher temperature has a wider distribution. So T4 is going to be the highest temperature. So the question is, based on the diagram, at which temperature will the reactant be consumed at the fastest rate? So the fastest rate will be T4 because there's just more particles that have enough energy to overcome this activation energy barrier, this dotted line right here. So T4 just has more particles with enough energy. So letter D. Okay, number 17. Okay, now with this, it's talking about what type of mechanism might happen for this. Now, the key on this one is that during the reaction, we get these X2 molecules that are produced. So we don't have that at the beginning, we don't have that at the end. That tells us that this X2 right here is going to be an intermediate. So that means it's got to be two steps, and then we're producing these X2 molecules as an intermediate. So that's going to be letter D. Okay, number 18 is talking about how this Ru will weaken this nitrogen triple bond and allow the reaction to happen easier. So it says the absorption of N2 molecules on the surface of Ru weakens the triple bond. So really what this is saying is it gives it a lower energy pathway for this reaction to happen. So that's what a catalyst does. Ru is a catalyst. So letter A. Okay, 19. We have a three-step mechanism with a symbolic form here. Okay, so the question is, which of the following models represents an intermediate in the overall reaction? So an intermediate is something that gets produced in one of the steps and is consumed later. So it's a product first and a reactant later. So this symbol right here, this would be an intermediate, but that's not one of the choices. Another one would be this. It'd be two nitrogens and an oxygen. There's a one right here, so it's a product first, it's a reactant later. So that's also an intermediate. So letter D is the correct answer. So with this one, we have a two-step mechanism, and the question is, which of the following is the rate law? So the rate law for a mechanism is based on the reactants in the slow step. All right, so here's our slow step. It's the first one. We have NO. NO now is a catalyst here, but we can have a catalyst in the rate law. So it's just one of those and one of these ozone molecules. So these are both going to be to the first order. So that's going to be letter A is the correct answer there. It's always the reactants in the slow step. 21, another two-step mechanism. And the question is, which of the following equations is the correct rate law that is consistent with the elementary steps in the mechanism? So again, we look for the slow step. In this case, there's two of these NO2s, so that means it's going to be NO2 to the second order. So it's going to be letter B. Okay, question number 22. The question here is, based on this information, which of the following statements is correct? So we have to look at all these. So it says the rate of the reaction will undergo a fourfold increase if the concentrations of both HI and IBR were doubled. Okay, so now we have to look at what's going to be the rate law. So the rate law is going to be the two reactants in the slow step. So H2 and IBR to the first order on both of those. Okay. Now HI is not in the rate law, so this isn't going to affect the rate. Okay, so it's not going to be A. We want something that's going to show this IBR and H2. And that's going to give us, if we double both of those, since it's first order to each of those, that means it's going to quadruple the rate law. I mean, not the rate law, but the rate. Okay. So here's H2 and IBR. That's our two reactants that are in the rate law. and we're doubling both of those, so we're going to get a fourfold or quadruple increase in the rate. So letter C is the answer. Okay, question 23, another two-step mechanism. Question is, which of the following is the rate law for the overall reaction? So in this case, we have this slow step. We have this O2 and this NO2, or just NO2, I'm sorry. Now the problem with this NO2 is an intermediate. Intermediates cannot be in the rate law. So that means we have to substitute this intermediate out with the reactants that turn into it. So that means it's going to be NO to the second order along with this O2 to the first order. So that means it's going to be letter C. Gives us that rate law. All right, 24. Another two-step mechanism where the second step is a slow one. We want to write the rate law for the reaction if the second step is rate determining. So this is another case where we have an intermediate that will need to be replaced. So in this case, this 2I is the intermediate. So we have to replace that with I2. So that means the rate law is going to have H2. H2 doesn't get replaced, but then I2 substituted in for this 2I. So it's going to be I2 to the first order and H2 to the first order. So that's going to be letter C. Okay, another two-step mechanism. So it says, which of the following mathematical equations provides a rate law that is consistent with this mechanism? This is pretty much the exact same question as the previous one. Here's our slow step. Here's our two reactants. X2 is an intermediate, so we have to replace that with X. Okay. No, X has a coefficient of 2, so that's going to be to the second order. So it's X to the second order, Y to the first order. So letter C. Question 26. Now we have a three-step mechanism. In this case, which of the following identifies the catalyst in the overall reaction and correctly justifies the choice? So a catalyst, excuse me, is a reactant in an earlier step and a product later on. And it would end up canceling out and not be in the overall equation. So in this case, we have H2SO4. It's a reactant in step 1. It's a product in step 3. So letter A is a choice. H2SO4 because it is consumed in the first step, because it's a reactant, and then regenerated in a later step. Okay, question 27. Okay, so we have a diagram above. So one of these is with a catalyst and one is without. Which of the following identifies the reaction energy profile for the catalyzed reaction? So a catalyzed reaction is always going to have a lower energy pathway. Now it doesn't matter if it's it has 4 different peaks, 4 different smaller peaks like that. It's the simple fact that it doesn't get to the same height as X. So this is a lower energy path to get from reactant to product. So Y has to be the catalyzed pathway. So let's see, it's either C or D. Increased number of transition states, that's not Y. It's because it introduces a different reaction path that reduces the activation energy. So we only have to have particles that have this much energy rather than that much energy to get from reactant to product. So it's letter D. Okay, and that's all for this progress check. All right, have a good day.